We are still in the free field theory with a Klein-Gordon Lagrangian. This gives a Gaussian path integral which we could solve with the effective action where D is the free propagator for real scalar fields. I'll now replace the expression for the propagator inside the expression for the effective action, and I will rearrange the integrals over x and y so that they are isolated. We recognize the Fourier transform of the source, while in the middle we have the Fourier transform for the propagator. K is a 4-vector with a time-like component corresponding to a frequency in time and a space-like component corresponding to a frequency in space. So the Fourier transform of the source J tilde of K gives us how the source acts on the field in terms of frequencies, both in time and in space. And the Fourier transform of the propagator tells us how efficiently a disturbance of the field at a given frequency k will propagate. So let's consider a source which acts on a given region of space and time. This source will induce a disturbance of the field which perhaps will propagate forward in time. In the dual space, the Fourier transform of the source has a given distribution in terms of frequencies, and the propagator selects which of these frequencies are going to propagate. We would like to know which of these frequencies are going to propagate, so for which value of k is my propagator going to lead to an efficient propagation of a disturbance of the field. So we would like to know what is the amplitude of probability for a disturbance of the field to propagate from a given region of space-time to another. And to get this amplitude of probability, the only tool I can use is the path integral I have defined at the beginning. So two things. First, I need to make sure that the amplitude of probability of the process I am interested in is indeed included into the path integral. Second, I need to find a way to extract this amplitude of probability from the more general one given by my path integral z. For the first point, notice first that we are in a free field theory. So if we manage to excite the field in such a way that a disturbance will propagate efficiently thanks to the propagator, because there is no interaction, it's likely that this disturbance will propagate forever. So the field will never come back to vacuum. And that's a problem because the amplitude of probability z of j is for a field going from vacuum to vacuum over an infinite time. So I need to make sure that at the end of time I go back to vacuum. In other words, I need to make sure that I annihilate every disturbance of the field I have created. So I need to split my source in two parts. The first part earlier in time, which will be indeed a source creating disturbance of the field, and another part at a later time which will annihilate this disturbance. We call it sometimes a sink. So J1 might still create disturbance of the field which will propagate in different directions of space-time. But only the one annihilated by J2 will return to vacuum and will lead to an amplitude of probability which is part of Z of J. While the other one will keep moving forward in time and the field will never return to vacuum. So these ones are not going to be part of the amplitude of probability Z of J. But for the field to return to vacuum after the source J2, we need to have J2 annihilating the very same frequencies that the one which have been created by J1. This means that in dual space, the Fourier transform of J1 and the Fourier transform of J2 must have a strong overlap in momentum k. If you want J to act a little bit like an active noise-cancelling headphone, imagine you have a source of noise in J1 propagating through the air, then J2 will just have to vibrate in opposite phase in order to cancel the noise created by J1, so acting like a sink. Of course, J2 could also create disturbance of the field which could propagate forward in time. But because there is no sink to annihilate these disturbances, they are not going to be part of Z, and therefore we can discard them. Remember that the action of the source in Z is only to change its phase. Therefore it's not Z so much which is of interest to us, but more the change of phase W of J, which we also call the effective action. W is quadratic in J, therefore we will have a term in J1 J1, one in J1 J2, one in J2 J1, and one in J2 J2. The term J1 J1 will describe a disturbance created by J1 and annihilated by J1 itself. It is called the self-interaction of the source. It's interesting, but it's not what I'm trying to extract from my amplitude of probability. So I will disregard the term in J1 J1 and the term in J2 J2. So let's consider the term in J1 J2. So W represents the change of the phase of the amplitude for a disturbance induced by the source in J1, propagating thanks to the propagator, and then annihilated later in J2. Although we are summing over all the possible temporal and spatial frequencies, we could choose J1 and J2 to select only part of these frequencies. We already noticed that J1 and J2 need to overlap, otherwise I can't annihilate what I have created. But for W to change, meaning that I will have an efficient propagation of a disturbance from J1 to J2, I need the propagator D of K to be non-zero for the frequencies excited by J1. So let's look at the propagator and try to see when will we have a frequency which will be efficiently propagated. Obviously this happens when k squared is equal to m squared, because in this case I have a division by 0 which blows up the propagator. Remember that k is a 4 vector. Just for fun, let's restore h bar and c. H bar omega is an energy and h bar k is a momentum. Then the condition k squared equal m squared for an efficient propagation of a disturbance of the field gives us. This is a well-known relationship between energy and momentum for a relativistic particle. We have just discovered what the experimentalist called a particle. This is a disturbance of the field which propagates efficiently with an energy and momentum obeying the famous relationship of Einstein.